Okay, here we go. Part 2. Questions so far? Pretty easy, right? Okay, so for all of that together, we can kind of come to this conclusion that the limit of a polynomial, so any polynomial, because what's a polynomial? Polynomial is just a combination of multiplying, exponents, adding, subtracting, right? That's what gives us a nice long polynomial. So since our limits work over all those different functions, then all we have to do for a polynomial, a nice polynomial, right, like our typical polynomials, is just direct substitution, and it will evaluate our limit. Okay, so nice and easy, just do direct substitution. Plug that guy in. We'll have 4 times 2 squared plus 3. And again, we'll just get, what'd you guys get? 19? Perfect. Okay, so again, I could split this up into 4, and then the limit of times x squared, and then the limit plus 3, right, that whole thing. But again, we can just say that for polynomials, we can just do direct substitution, okay? So again, that's all that this is saying here. Notice that the limit as x approaches 2 of the polynomial function, blah, 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 is simply the value of p at 2. This direct substitution property is valid for all polynomial and rational functions with non-zero denominators, okay? So that's going to work for any nice polynomial and any nice rational as long as the denominator doesn't equal 0. So that's all that it says in this chart down here. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is just equal to p of c. Basically, it just says you can do direct substitution. Okay. If r is a rational function given by r of x equals p of x divided by q of x, and c is a real number such that q of c does not equal 0, right? Denominator cannot equal 0. Then, again, the limit as x approaches c of r of c is just, or of r of x is just equal to r of c, which is the same as p of c divided by q of c, right? So again, we're just doing direct substitution. Okay, so these are nice and easy. When you've got a polynomial, a rational, just plug them in. So let's try example 3 with a nice rational. Notice here, if I take this 1 and plug it in, it doesn't make my denominator 0. So I can do this. Okay, if it makes your denominator 0, we got to do a different method. Okay, since it doesn't make my denominator 0, all I have to do is direct substitution. Go ahead and do it. What do you guys get? 2. 1 plus 1 plus 2 over 1 plus 1. The limit of that function as x approaches 1 is equal to 2. Nice and easy, right? All right, let's talk about what happens if we have a radical function. Turn the page. All right, so a radical says, here's our theorem. Let n be a positive integer. The following limit is valid for all c if n is odd, right? Because if I've got a cube root or a fifth root or a seventh root, I can take the square root of or the cube root of a negative, right? So if my n is odd, that's my index, right? If my index here, nth root, is odd, then I can use it for any c, positive or negative. It's only going to be valid for positive c's if n is even, right? Because you can't take the square root. We don't want to deal with complex numbers here, okay? So we can only take the square root of positive numbers, the fourth root of positive numbers. It will be direct substitution again, right? Notice all that they're doing is plugging in the c, and you get the nth root of c. Okay. This first one wants us to do a little composition example. So rewrite f of s as the composition of two simpler functions. Remember function composition? F of g of x, g of f of x, okay? With the little o, or when we put double parentheses in there. So what we want is we want to break this guy down into two functions. What would be my two functions? Let's call them g and h. What would the function g be? You can go either way. Yeah, let's just do root x for that one. And then what would h be? X plus 1, right? So then would this be g of h of x, or would it be h of g of x? G of h of x, right? The other way you could write this is with that little o, right? Remember that? G of h of x. Okay. So we're taking the square root of this other function. Okay, so we're taking h and we're plugging it in to g. Remember how that worked? Okay, so just a reminder on function composition, because now our next theorem talks about the limit of a composite function. So here we go to the next one. If f and g are two functions such that the limit as x approaches c of g of x is L, and the limit as x approaches c of f of x is f of L, that means they're composite functions, then the limit of the composition is just going to equal f of the limit of that inside one, okay, which is just f of the limit. Okay, this is kind of like, oh, what do you mean? Let's go through the example and it'll make more sense. Okay, but just saying that function composition also carries through for the limits. So here's example 4. All right, so what is the limit as x approaches 0 of x squared plus 4? 4, we're just going to plug it in. This is direct substitution. We have a nice polynomial. I can just plug it in. 0 squared plus 4, I just get 4. And what is the limit as x approaches 4 of the square root of x? 2. Again, we just want the positive square roots here. Then it follows that the limit as x approaches 0, bless you, of the square root of x squared plus 4, so now I'm doing composition, is just going to equal 2, right? That's it. Okay? That's all that this happens to do. That's all that this is talking about. That makes sense? We're just plugging this one into there, and we're plugging this into that, and then we're plugging that into that, right? So it's just following through. Use the same reasoning to find the limit as x approaches 3 of the cube root of 2x squared minus 10. Go ahead and try it. Tell me what you get. Are you just doing direct substitution, or are you actually decomposing? Direct substitution. Cheaters. Okay, you can use direct substitution. Yeah, you're on my flojos. We can plug it in. You get the third root of 2 times 9 minus 10, which is the third root of 18, minus 10, which is the third root of 8, which is 2. But let me show you how to use it with the composition part, just to see like if that made sense. So basically, we would start with the limit as x approaches 3 of the inside function, 2x squared minus 10. Do direct substitution here, all right? So you just get 18 in this answer, or 8, what do we get? 18 minus 10, so we get 8. And then take the limit as x approaches 8, that now becomes your c, of the function the cubed root of x. So then I can plug that in now, and I get the cubed root of 8, which is just equal to 2. Basically, you're taking the answer to the first one, using that now as your input, or your C value, to plug it in and get your next one. Same answer either way. Okay, but just kind of showing you how it looks with composition. Okay, hold on, I might need to pause again. Time-wise, yeah, I'm going to pause.